So if I'm going to write down the solution to this, I'm going to use this form here. So I'll just write this here, y of t equals a over b minus y0 e to the minus bt. So then I'm going to, if I mimic this, I've got an L over T instead of a Y. My A is going to be equal to K L infinity. My B is just going to be equal to K. And then I'm going to subtract here. Again, these cancel. So this is just going to be L infinity minus L0 times e to the minus KT. So if I now reorganize terms a little bit, I will get, this will be equal to L infinity into 1 minus e to the minus KT minus L0 e to the minus KT. Okay, so one of the tricks in this is to treat this in a slightly different way, and that is, if you have a look over here, and you work with an arbitrary constant, then if the initial condition, the initial size is 0. Now, the initial size of an organism is never 0 unless you go to the point of conception. So if you're looking at a fish, the egg usually has some mass. At the point of conception, you can say it's so close to 0 that we can treat it as 0. So you can think of this as time of gestation. So if you choose the initial condition to be 0, then you can get this funny interpretation where C is equal to KT0 L infinity. So it's like this time that you go back is a time that's equal to an amount T0. And if you were really stupid, you could say that's the gestation period. I say really stupid because you don't expect an egg to be growing at the same rate that the hatched egg grows at. But for some reason, biologists want to do this. I don't know. They want to make this kind of thing because it's so neat, packaged up. But anyway, so if you make C equal to the KT0, then you can write it in this form. And in that form, T0 is then interpreted as sometime before 0 that the organism, that you start looking at it when you get its growth curve over here. And you can interpret that as a kind of a gestation period, or a virtual gestation period. But anyway, be that as it may, that is the von Bertalanffy growth equation. And in this form, you can say this is how fish grow in length. And as I said, if you're looking at how do fish grow in biomass, and you assume that in each of the dimensions, they grow at a similar rate, so that the rate at which they grow is controlled by the difference between the current value of that dimension and the maximum value of that dimension. If you have the same parameter k in all the dimensions, so if you say width, length, and height are all growing in the same way, then you can say, okay, I'm just going to make this cubed, and I'm going to have mass instead of length in there. Now that, again, approximately true, but the von Bertalanffy growth equations for weight often lead to biologists fitting a curve that looks like this. So this may be weight W of t. You start out at some W0, and you go to some W infinity, and then you have W of t is equal to W infinity 1 minus and some constant e to the minus kt, and you can have another power here, let's say h. And this constant is set by saying that W of 0 is W infinity 1 minus the constant to the power h, and then you can calculate, and you set that equal to W0, so you can calculate what that constant is. I'll just put capital C here. So you can calculate what that constant is to satisfy the initial size. If you look at data and you fit data to a curve like this, you don't usually get h equals 3. You usually get h equals something a little less than 3. Like somewhere between 2.7 and 2.8 is very often what you find in the data. So what that tells you is that when individuals grow, they grow in all dimensions kind of at an approximately equal rate, but not quite. And that's because if you look at babies, for example, they probably get longer, a little faster than they get wider. And so when they're small, they have these big heads and they look a little rounder. And then as you become an adult, you get a little longer. And that's because the length one, that K is a little bit larger than the width one. And that's also got to do with the fact that not everything in your body is going to grow at the same rate. So, for example, your brain is relatively big compared to the rest of your body, and some of your organs are relatively big compared to the rest of the body. And so not everything scales in the same way. And for example, if you had a look at the cross-section of your bones, you can have very thin bones if you're small, but as you get bigger, your weight is increasing like 3 dimensions. But the cross-sectional pressure on the bone is increasing like in 3 dimensions, but the strength is increasing like in 2 dimensions. So your bones have to get relatively thicker compared to your total mass as you get bigger. So these are all things that you can study in physiology. Now let's have a look at this problem. So this is a lake pollution problem, which I'll just kind of run through. Let's do it here. And so in this problem, we have a lake. And let me draw it. So, yeah, this is a lake. And it says that in this lake, there's 100 cubic kilometers of water. That's quite a big lake. And what's coming into this lake? It says the lake is fed by rivers and tributaries at the rate of 48 cubic kilometers per year. But pollutants are also entering this lake. So you've got some water, and you're saying this water is pollutant water. I'm not defining what these pollutants are. I'm not defining what the concentration of the pollutants are. But what I want to know is that for every unit of pollutant water coming in, how does it get, what proportion of that water remains in the lake? Because some water is going to go out. Some of the pollutant water is going to go out from the lake. So we're going to assume that 2 cubic kilometers of water are flowing in per year. Now, sometimes water is measured, it's measured in cubic meters, but if it's a lot, then cubic kilometers are useful. But also in American systems, it may be measured in acre feet. So acre feet is like if you take an area of an acre and you take it a foot deep, that volume is an acre foot. Maybe millions of acre feet. It's just a measure. Scientists don't like to work in these kinds of measures. They like to work purely in, what do you call it? Kilometers and, metric system. Metric means measure, so kind of self-defining, metric system. Okay, so we're going to assume that the amount of polluted water at any time in here is given by a variable y of t. Now this is year, so I'll put yr. So it's a different y, but it's actually year. But the variable here is y of t. So of the 100 kilometer cubed water in here, y of t kilometer cubed is pollutant water, and 100 minus y of t is fresh water, but it's perfectly mixed. So these are called mixing models because in these models we assume that whatever comes in here is instantaneously mixed very rapidly. You can imagine that there would actually be some gradient so that what you find over here initially is different to here because it gets mixed as it moves through. But if you have something in there that's whirling around that's mixing it, then everything would be well mixed. So it depends on the time scales, but on the time scales we're talking about, we can assume that if there's enough wind and things going on, that it's sufficiently well mixed that this will work. So what we have here is, coming in we have 50 meters, 50 km squared per year, and we assume that what goes out over here is the same. And we assume that this is well mixed. So this is what comes in, and this is what goes out. And what goes out is a proportion of this, and a proportion of this, and that proportion at any time is given by y. And so, in this 50, what proportion of it is fresh and what proportion of it is polluted? So the proportion polluted is going to be y of t times 50 divided by 100, because this is the proportion in there. So the proportion is y over 100 is of this, and 50 is what's coming out. So this is equal to y over 2. So if we have a look at an equation for dy dt, what's coming in is 2, and what's going out is y over 2. And initially y is 0 if the factory or the pollutants are just starting up. So that's the equation, and if you integrate this, and you solve it, using this technique, you'll get y of t is equal to 4 into 1 minus e to the minus t upon 2. So if you take this equation and you set y0 equals 0 and you use the formula, then this was what the solution will be. So you can go through that and check it. So the question is, how much does this lake ever reach the true percent level of polluted water mixed in with fresh water, and if so, when? So you want to know when this number, if it starts out at 0, is going to reach the 2% level. So the 2% level would be y equals 2 out of 100. So in other words, you want to solve for t when 4 into 1 minus e to the minus t upon 2 is equal to 2. And if you go through the calculation in the textbook, you'll see that if you solve that, just going through these equations over here, that t is equal to 1.39, which is approximately after a year and 5 months. So these linear equations, yeah, so this is a minus sign over here. Okay. Now this is a fairly simple model, and you can integrate them, so there's no reason to use NOVA to solve these models. These models only become interesting when you have, instead of just one variable, you have several variables. So in your homework assignment, we'll come back to this muscle, blood, brain, morphine concentration compartmental model. And let's just switch off the lights over here. It's okay. So we can look at this a little better. So as I said to you, this arises when you have 3 compartments, and the flow out of X is equal to the flow into Y, the flow out of Y is equal to the flow into Z. Within Z, you have the molecules being degraded, so the body is metabolizing them and getting rid of them. And then you have blood dripping into the system, morphine dripping into the system. And then initially, you can have an injection into the muscles, and you can have nothing in the blood in the brain, and you can say, okay, how does this thing gear up? So you can build a basic NOVA model. So a NOVA model of this would have a muscle, blood, and brain, an X, Y, and a Z. And you'd set this up so that you get the right-hand side just being minus X over 1/8. And you'd also have an amount you can inject that, although you can't see it, this dotted line goes into here, which sets up the initial condition. Here, this dotted line goes into here, which allows you to set a value for B. Then in this equation, you can have this right-hand side having X over 8, and then you have a term y minus y over 8. And I can bring up this model for you. Let's do that in Nova. The reason why I'm showing this to you is because we're going to do something interesting with Nova that you haven't really done so far. So this is what we have. Now, in this is a little different from this picture over here. In this picture over here, what I've got is these are sliders. But instead of having sliders, I can make them into pins, A and B. And this output, instead of graphing this output directly, I can make them into pins, X, Y, and Z. And X is the amount, is the value of the muscle state, Y is the value of the blood state, and Z is the value of the brain state. Do you know how to make these pins? Okay. I'll show you how to do that. Something's happened to this model. So it's not going to work. Oh, it is working. So if you come back to this level over here, you could just have a graph. So let's put in a graph. Okay, and this is output. And in this graph, what I could do is I could plot the blood and the brain. I could plot the blood, and I could plot the brain, and I could plot the muscle. Okay. And then I could run the model at this level, and you'll see that I get what starts out in the muscle decays over time. Now, these are all different axes. I might want to make all the axes the same. So let me set the axes so that they're all the same. And we'll go from 0 to 10. And we'll set that, okay? And then we'll capture load exec. So actually this goes above. And these are not sliders, but if I had sliders, then I would have things around that I could mess around with and play around with. Now what you can do is, instead of having sliders, you can have input and output pins. So here's an input pin. Here's a pin. And you can give it the name input pin, okay? And if you see over here, for some reason these input pin names are missing and it's still working, so I don't know what's going on, because I was messing around with it. But it seems to know what it's doing, but not showing the right things here. But anyway, what happens is that if you want to get two versions of this model over here, so you have these input pins and you have these output pins. So this X is actually the muscle. This Y is actually the blood. This Z is actually the brain. And I'm going to get rid of this because I don't want it at this level. So when you build your model, instead of having a graph as an output, you have an output pin that is the muscle value, an output pin that is the blood value, an output pin that is the brain value. You have an input pin that, instead of a slider, puts in the value of the drip. And that determines the initial condition. Actually, if we go over here, you'll see the initial condition is A. And if we go into this equation over here, there's B, which is the drip, and there's the muscle term, and there's the blood term, okay? So all this version of Nova's done is it's taken away these dotted line connections that you often see. Now you go to the next level, and at this level, what you do is you grab this and you pull it out. And when you do that, it says, this thing over here represents this model. They're the two input pins and the three output pins. So if we have a look at this, it's got two input pins and it's got three output pins. If we go into here and we open this up, it says that the A is something that I'll call my inject 1. And inject 1 is the value that I'm going to set to inject into my first system. Inject drip 1 is what I'm going to put. So if I go here, I've got A is going to be inject 1, and then I'm going to go B, and that's going to be drip 1. Okay, and then I'm going to go here to the second example, the second repetition of this, and I'm going to say my A is going to be inject 2, and my B is going to be drip 2. And the reason why I do this is because I want to run the same model twice with different values. So for example, what I'm going to do here is I'm going to say what happens if I inject 5 milligrams of morphine, but I have nothing in the drip, compared to if I inject nothing and have a drip with 0.1 milligram per hour. So the reason why I've done this is that I can have two versions of the model side by side, and I can run them at the same time. And in this third graph over here, so in this graph, I'm going to plot morphine, I'm going to plot the X, Y, and Z values for the first model. And in this one over here, I'm going to plot the X, Y, and Z values of the second model. And in this one over here, I'm going to plot the Y value of the first model and the Y value of the second model.